So first let us define what a gridded ring is. Yeah, recap. So we write gridded ring H star X as this particular structure of cohomology groups. So we want to talk about relative cohomology and applications. So take a space K which is covered by two sets L1 and L2. So this is the following map we get. Now this is clear from the definition of cup product itself. Yeah, if a co-cycle vanishes on HP, then automatically it will vanish on HP plus Q by the definition itself. Similarly, if a co-cycle vanishes on HQ, it will again vanish on HP plus Q. So let us write down the applications of the above map. So let us write down this. K is covered by two sets L1 and L2. L1 is contractible and L2 is contractible. So we are saying they are homotopically equivalent to a point, yeah, by deformation, retraction. So the question is, what is the multiplication in the ring H star K? So let us address that. So first we build a long exact sequence. Yeah, take some index P1 and start drawing the long exact sequence. Now this is 0 because L1 is contractible space. Similarly you do KL2. So again this is 0. So we have epimorphism right here and here. We have surjective maps. So the elements of HP1K come from HP1K, L1. Similarly HP2, KL2 elements contribute to all elements in HP2K. So beta 1 comes from alpha 1, beta 2 comes from alpha 2, precisely because the map is a surjective map. So we want to talk about alpha 1 cup alpha 2. This will get mapped to beta 1 cup beta 2. So we want to find out what beta 1 cup beta 2 is, and beta 1 and beta 2 are some arbitrary elements, yeah, in some gridded part P1 and P2. So the secret lies in alpha 1 cup alpha 2. So you know by multiplication it will land in P1 plus P2. Now K is equal to L1 union L2. So therefore this part relative cohomology would be 0. Yeah, K modulo itself will give you 0. So this 0 is what gets mapped to beta 1 cup beta 2. So that means beta 1 cup beta 2 is 0. So cup product is 0 for any two non-zero elements in the graded ring H star K. So yeah, so you take any two elements, you take their cup product, it will be 0 in the graded ring H star K. Now what is this kind of space K is? Yeah, I want to give some natural examples. So natural example is that this space K has to be covered by two sets L1 and L2, both of them contractible to a point. Okay, so a simple example is the suspension map. Yeah, so suspension of K, you know, looks like this. You have K first, which I have drawn in yellow. This is the space K, and then you put cone on the top of it and bottom of it. Yeah, so let us put a cone on top of it. and cone on bottom of it. Now suspension of K consists of two contractible parts, the top cone and the bottom cone. So take top cone as L1, bottom cone as L2, and obviously the center part is K. So suspension of any space K, and if you take its gridded ring associated, the cup product will always be 0. So cup product in this gridded ring will be 0. So it has trivial cup product. So now we want to apply what we have just used. So let us talk about multiplication in wedge products. So first note, we had covered wedge products in homology. Yeah, so in homology we knew that you can take wedge products and it will split as direct sum. Now that idea carries over to cohomology too. Yeah, or you can just do it by cohomology axioms. So you can either use the idea in homology, use the universal coefficient theorem, or just see cohomology axioms again. So you can stop here and have a look at cohomology axioms in Hatcher, and I think it is the third axiom, and then you can, by that axiom, you can say, so this is the structure. Now we want to talk about how do we use cup product in such a gridded ring structure. So the cup product would be x1 comma x y1. You have to make a cup with x2 comma y2. So yeah, so you see that there are no cross products like x1 cup with y2 is 0. Yeah, why is it 0? Because any such cup product will have to lie in the intersection of these two gridded rings, which is 0. Similarly for the other part, y1 cup x2. Now I want to talk about retractions and cohomology rings. So first we have to talk about some general principles. So consider this following sequence. You go from a group G to H and then to group G. You go first apply a map phi and then you apply a map psi. This application is such that the composition is ID. Yeah, so first apply phi and then psi, you get ID. So the claim is this group H can be written as image of phi plus kernel of psi. So proof is really easy. You take an element h of h and you write it as the following. So this h you first obviously write as image of phi because that is what you want to use. So you write it as image of phi plus now h minus, so standard way of writing it. Yeah, so we have to prove that the second part h minus phi psi h is in the kernel of psi. Yeah, this is in the kernel of psi. So what does it mean? I apply psi to h minus this map, it should be 0. So you get phi h minus, but phi and psi gives you id. So what you get is phi h minus phi h, you get 0. So that is true, and we are done. Now we will apply this above construction to a topological situation. You take a map A, inject it into space X, and then it retract it back to space A. So first we form the homology groups. So homology groups keep the arrows in the same direction. So yeah, so now we apply the above result. Yeah, so it's always image of the incoming map and kernel of the outgoing map from X. Yeah, so incoming map is I and outgoing map is R star. So what about cohomology? First thing is cohomology, arrows get reversed. Yeah, cohomology is contravariant in nature. We have already talked about this. So again, what is the graded ring structure? It has to be image of the incoming map, which is R star, and kernel of the outgoing map, which is I star. Yeah, so this I star should be superscript. Yeah, you should have R here, R star here, and the first I star, this should be superscript. Okay, so this is important. Now there are two more things I want to talk about. This image of R star here in the cohomology part is a ring. Very important. So we have to prove that image of R star. So you go from H star A to H star X. So this image of R star is a subring. Yeah, you know, subring is a ring in its own right. So you could say it's a ring or a subring. But we have to prove the following. Yeah, so R star alpha cup with R star beta, where alpha and beta are obviously elements of the graded ring on the space A. So yeah, so this relationship, so you take any two elements, you take their cup product, you still end up in the graded ring of X. So that shows it's a subring. Then kernel of I star is an ideal. Now again, this ideal, again it follows the same structure. Yeah. So now you're taking alpha beta in the graded part of H star of X. So you get I star alpha cup beta, but if I star alpha is 0, then this cup product will be 0. Yeah, because the multiplication, the cup product is nothing but ends up in a ring multiplication by definition. Second part is 0, I star beta is 0, then I star alpha cup beta is 0. And this is important to remember. So now let us do some application. So the first application is this. This wedge product is not a retract of these product of SP times SQ. Now this can be proved by the previous result. So we have the space. So A is the space which is the equivalent to SP wedge SQ. Yeah, on the previous slide we had written A. So we replace A with SP wedge SQ, and X we replace with SP times SQ. So This is a first inclusion map and then retract back to SP wedge SQ. Now we put the graded ring structure on it. Just like we did in previous slide. And from here the story begins. So the idea is that we will show the contradiction arises because image of R star will not be a ring. So let us write down first the elements. So what are the elements here? So the elements will obviously, the cohomology of a sphere exists in only dimension P, dimension Q and dimension 1. Yeah, all other cohomology groups of a sphere are 0. What about this part? Here obviously 1 exists. It again exists in dimension P, dimension Q, but it also exists in dimension P plus Q. Yeah, this we have already seen before. So you have to, for this graded part, you have to compute cohomology for each and every part. So I have written down the generators of the graded ring H star SP times SQ. So you can see the kernel of I star is nothing but alpha P cup with alpha Q. Yeah, because this term does not exist in the graded ring H star SP plus H star HQ. Yeah, because alpha P cup alpha Q, there is no SP plus Q essentially. What is image of R star? Again, image of R star is nothing but the elements in H star SP times SQ which are not in kernel of I star. Yeah, so since kernel of I star contains alpha P cup alpha Q, rest of the elements are in image of R star. So, but this shows that image of R star is no longer a ring because you take two elements alpha P cup alpha Q and they are not in image of R star, and that is a contradiction. So another example is RP2 is not a retract of say RP3. So suppose, again, we will use precisely the same plan as on the last slide. Yeah, so the idea is simply this: you construct this chain inclusion map and a retraction map, then we put the graded ring structure on it. Now graded ring structure consists of separate parts, but we take cohomology coefficient as Z2. Yeah, so this makes life much easier. And again we will show that image of R star is not a ring. So what is the graded ring structure here? Yeah, so it contains 0, it contains 1, it contains alpha, alpha square, alpha cube, yeah, corresponding to the graded parts. Because a cohomology group exists in every dimension, we have a H superscript 0, H superscript 1, H superscript 2, H superscript 3. Similarly, I have written the RP2 structure. So what is the kernel of I star? Obviously, alpha cube has to go to 0. Now you can see if kernel of I star is there, what is the image of H star RP2? So now the image has to be only 1 alpha and alpha square. Yeah, so this is the image. So obviously alpha cup alpha square does not lie in R star. So it does not lie in image of R star, and therefore it is not a ring. And therefore we have a contradiction. So RP2 is not a retract of RP3.